Hey everyone, this video was made in part of our Principles of Chemical Engineering and Chemical Engineering Fluid Mechanics courses for the Jan 2025 semester, and in this video we are going to be discussing our design for an acetone production plant. My name is Ruhan Srirama and let's get straight into it. Moving on to the first part, which is Principles of Chemical Engineering, this is our design for an acetone production plant. As you can see in the process flow diagram, there are 6 units which consist of reactive vessel, which facilitates the dehydrogenation process from isopropyl alcohol to acetone. We have a scrubber which removes excess hydrogen from the product stream. We have 2 condensers which is used to convert vapors that may exist in the stream into liquids. We have the distillation column which separates acetone from the reaction mixture based on their boiling points. And lastly, we have the storage unit, which is used to store acetone that is produced from the process safely. In this video, we are going to be focusing on 2 of these units, which is the reactive vessel and also the distillation column.
By taking a basis of 50 kmol per hour, we obtain that 32.5 kmol per hour of isopropyl alcohol and 70.5 kmol per hour of water as a feed. As a efficiency of reactive vessel is 95%. Water is a catalyst, it not be consumed or chemically changed, so it will be the same as a inlet. For more fraction, we obtain it from dividing the molar flow rate to the total of molar flow rate. For getting the mass flow rate, molecular weight of the substance of 1 kg substance per mole times the volume flow rate of the substance. In this reactive vessel, we obtain the mass flow rate is 2268.6 kg per hour.
Next is the non-reactive distillation column. Some of the assumptions that we've taken into account is the total molar flow rate of the inlet stream is calculated as 67.5 kmols per hour. More assumptions include that 90% of acetone from the inlet stream evaporates and is collected at the top product stream, while 100% of the water from the inlet stream leaves the distillation column through the bottom product stream. The ratio of isopropyl alcohol in the top product to the bottom product is 1:2. After calculation, these are the molar flow rates and compositions of distillation column. And after using the mass flow rate equation, these are the mass flow rates given in kilograms per hour with their mass fractions. Now let's discuss the energy balances. We'll start with the reactive vessel. Now obviously the reaction is dehydrogenation of IPA to form acetone as well as hydrogen gas. So the reference state is at 25 degrees Celsius at 1 atm. The assumptions are that the temperature of the inlet is 325 degrees Celsius and the temperature of the outlet is 350 degrees Celsius as per our references, and the pressure is assumed to be constant at 2.32 atmospheres. All standard values, especially standard heat capacities, are taken from the important appendix. Some standard heat capacities are also taken from the NIST webbook. As for our calculations, we took many steps. In the end, we found the extent of reaction of dehydrogenation of IPA to acetone, as well as the heat of reaction based on the heat of formations of all the constituents in the reaction. Our final enthalpy that we got is 358.6114 kilojoules per second. Next is for the non-reactive system, which is the distillation column, and the reference states are provided as follows. The references and assumptions that we had was that the inlet temperature is given as 15 degrees Celsius and the overhead temperature is given as 79 degrees Celsius. Since the bottom stream is liquid, hence the temperature is assumed to be 50 degrees Celsius such that it does not reach the boiling point of isopropyl alcohol and acetone. The pressure is assumed to be constant and the same as before at 2.32 atmospheric pressure. So we did many calculations once again and obtained this table, which includes the molar flow rates of all the components as well as the enthalpies of each component, and we obtained a final enthalpy of 328.7955 kilojoules per second.
Okay, so now let's move to the fluid mechanics part. In this part, we will explain the fluid, the pressure drop between each pipeline, and also our strategy to send the acetone into storage tank. My name is Inosli Anas Medan, and I will explain furthermore into the pressure drop of the fluid. So for the introduction, the pressure drop calculation. In this part, we will be using Bernoulli's equation to calculate the pressure drop for each pipe. We have 7 pipes in this part, which only 6 pipes, 1, 2, 3, 5, 6 and 7 consists of incompressible fluid, while pipe 4 consists of gas, which is compressible fluid, making the pressure drop negligible. The following slides that I will show you is our detailed calculation of the pipes. So now for understanding the pipes, you can see from the first diagram, this is our drawing of the pipe and also the table, which show pipe 1, 2, 3, 4, 5, 6 and 7. So here's the equation that we use to find the pressure drop in every pipeline. So the first one is the volumetric flow, where from what we get the mass flow rate, we divide it by the pressure at the density to find the volumetric flow. Then we use that to find the velocity, which connected to find the Reynolds number. From the Reynolds number, we can know if the fluid is laminar or turbulent. Depending on which of those two, we can find the friction fraction of each pipe. Then we can find the head loss, and also by then we can substitute into the last equation, which is the bottom, to find the pressure drop in each pipeline. So from this, we put it into a table to make it more easier to see. Then we can see that from each pipeline they have a significant pressure drop, which we can use to find for our strategy in the next part.
Today, I'll be walking you through the technical specifications and justifications for the components of this system as outlined in the table. Each element has been carefully selected to ensure optimal performance and durability. First, the material used is 316L stainless steel. This choice is ideal because it offers high resistance to corrosion, particularly from ethyl acetate and other organic solvents. It's durable and perfectly suited for industrial environments. Next, the pipe has an inner diameter of 74.5 inches based on Schedule 40 standards. This large diameter minimizes friction resistance, allowing smooth fluid transport throughout the system. Moving on, the pipe length is estimated at 12 meters, which represents the distance between the condenser outlet and the storage tank. Additionally, there is an elevation of 8 meters to account for the vertical height difference between these 2 points. For fittings, we've incorporated 2 90-degree standard elbows and a swing check valve. This ensures smooth directional changes in the flow and prevent backflow into the pump, maintaining system efficiency. The storage tank is also made from 316L stainless steel. This ensures long-term resistance against ethyl acetate while preventing contamination of stored materials. Finally, we've chosen a centrifugal pump for this system. It's highly efficient at handling high flow rates while ensuring steady fluid movement throughout the process. In summary, each component has been carefully selected based on its functionality and compatibility with ethyl acetate handling systems. These designs ensure durability, efficiency, and reliability in industrial operations.
In conclusion, this project successfully applied chemical engineering principle and fluid mechanics, as well as mass and energy balance and unit operation to design an efficient acetone production process. By optimizing key factors such as temperature, reactant flow rates, and equipment selection, we ensure an efficient process design. This project demonstrates a holistic approach to process engineering, balancing efficiency and cost effectiveness, while encouraging future improvement in acetone production.